So let's kick this explainer off with a question that'll usually get you laughed right off a job site. Would you pour fresh concrete right over a pile of rusted steel rebar? If you said, absolutely not, well, you're definitely in the vast majority. But you know what? You might also be wasting thousands of dollars, completely wrecking your project timeline, and, ironically enough, weakening your structure.
Welcome to the Explainer. Today, we're looking at the real-world field reality behind reinforcing steel. Because as a senior structural engineer who has walked, countless job sites, I'm going to let you in on a little secret that makes a lot of folks uncomfortable. A little rust? It's actually your secret weapon.
Section 1. The Great Rust Myth and Rethinking the Visual Bias Against Corrosion.
Look, we've all been there, right? You see a fabricated column cage sitting out in the weather looking all brown and crusty. Our immediate, very human instinct is to look at that oxidation and assume the material is actively decaying, like it's fundamentally compromised and just entirely unfit for a high-stakes engineering project.
And when that visual bias kicks in, field inspectors understandably get pretty nervous. They'll pull out general code statements like this one from ACI 301, demanding perfectly clean steel that's free of materials deleterious to bond. But man, that single, rigid interpretation, it leads to massive delays and incredibly expensive sandblasting or wire brushing operations, literally just to make the steel look shiny again.
But here's the thing, that visual bias is completely tricking us. We associate rust with decay, assuming it destroys the concrete steel bond. But the absolutely crucial point here is that we are confusing catastrophic section loss, where the bar literally shrinks in mass and size, with standard atmospheric oxidation. When buried in concrete, those two conditions behave entirely differently.
Section 2. Science of Mechanical Interlocking and Why Rougher is Actually Better. So, for reinforced concrete to actually work, the two materials have to act as one, and that requires mechanical interlocking. It's the physical bonding of materials through surface roughness and pitting. Think of it kind of like industrial Velcro, or the deep, aggressive treads of a hiking boot really gripping a rough, rocky trail. The rust creates this microscopic, coarse pitting on the surface of the steel that allows the liquid concrete to flow in, harden, and literally bite right into the bar.
And the reality is honestly stark. A weak bond comes from a shiny, ground and polished steel bar. It's just way too smooth. Under high stress, it'll slip right out of the concrete. But a superior bond? That comes from a naturally rusted, rough, and pitted bar. In fact, research shows a rusted bar can handle up to 4 times the stress capacity of a polished one. 4 times!
Now, the math behind this is super fascinating. Research pinpoints the absolute sweet spot for maximizing this bond strength. It's a corrosion ratio of 4% or less by weight loss. Let that sink in. That means a healthy, controlled layer of natural oxidation isn't just acceptable. It mathematically optimizes the structural integrity of your entire concrete project.
Section 3. Trust the building codes. The receipts from over a century of engineering research.
Believe it or not, engineers have actually known this secret for well over 100 years. If we trace all the way back to this landmark 1909 study from Whitby, it was definitively proven that the bond between concrete and a bar covered with a firm, hard rust significantly outperforms a plain, clean, unrusted rod. We've known this for over a century.
And modern codes absolutely reflect this science, even if folks out in the field misinterpret them. Major authorities like AASTO explicitly state that bonded rust or mill scale will not be cause for rejection. The only real caveat, the bar still has to meet its minimum physical dimensions. Basically, as long as the steel hasn't physically shrunk below tolerance, bonded rust is totally structurally sound. Section 4. Good rust versus bad rust, and visual assessment in the field.
Okay, so here's the trick to actually telling the difference when you're out walking the site. Whether it's that light red and orange dusting you see on the left, or the heavier, thicker brown pack you see on the right, both are completely acceptable. The ultimate deciding factor is that the rust must be tightly adhered and the bar's ribbed deformations must be clearly visible and fully intact.
Now, that being said, there are absolutely unacceptable field conditions where you must reject or clean the bars. If the rust is loose, flaky, or peeling off in big sheets, that creates a slip plane and completely ruins the bond. Also, if the bar was exposed to a saltwater or brackish environment, it traps chlorides that'll just continue to corrode the steel inside the concrete. Obviously, if it's covered in job site grime like mud, form oil, or paint, that's gotta go.
And finally, if the rust has caused severe pitting that actually eats away the physical ribs, the deformations of the bar, it is absolutely no longer structurally sound.
But if you do find yourself in a situation where you need to clean a bar, listen very closely here. Do not overclean it. Excessive aggressive cleaning with wire brushes or flapper wheels can actually polish the bar. Remember our Velcro analogy from earlier? Overcleaning ruins that essential surface roughness, destroys the mechanical interlock, and completely sabotages your structural integrity. Seriously, don't do it.
Section 5. The Job Site Mallet Test, a practical guide to field inspection.
So let's get practical. Here are 3 super simple steps for checking your rebar. First, just visually inspect the deformations to ensure those raised ribs are sharp and not eaten away. Second, rely on normal handling. The typical rigging, lifting, and placing of the bars will naturally just knock off most of the detrimental loose rust. And finally, the mallet test. Just give the bar a solid, light knock with a mallet or a hammer. If the rust stays tightly packed and adhered after the strike, that bar is good to go.
If your site material looks like this after a quick strike, with tightly adhered rust and clearly defined ribs, you've got the absolute perfect surface profile for a maximum strength bond. You don't need to touch it. Leave it alone. It is perfectly prepped for concrete placement.
So, I want to leave you with this final thought. Are we finally ready to stop fighting nature and let controlled oxidation do the heavy lifting in our structural foundations? The next time you see a little brown rust on the steel, ask yourself, why are we spending so much time and money to fight a natural process that actually makes our engineering stronger? Think about that next time you're out on site, and I'll catch you in the next explainer.